Welcome to Introduction to Structures. This is lesson 15. We are going to introduce an structure called 3-pin frames. This is an isostatic structure and is the first video where we're going to discuss a two-dimensional structure that is more complex than a beam, let's say a simple supported beam or a cantilever beam. So I'm going to use this example to make a recap about the most fundamental concept in structural analysis, and we're going to see a comparison between what is a simple supported frame and a 3-pin frame to see the difference in terms of internal forces and stresses. So let's start doing a sort of recap about the fundamental concepts in a structure. So if we still thinking about the simple supported beam and a cantilever beam, we say that these two structures are isostatic because the number of degrees of freedom in two dimensions are equal to the number of restrictions we are imposing these beams, and this is the reason why they are called isostatic, because iso means equal. So 3 degrees of freedom have the freedom that any beam has in the two-dimensional space, and actually it's not only for beams, it's for every structure. So this beam is able to move in the horizontal direction, vertical direction, and is able to rotate. But when we introduce this pin support that restricts the two movements or horizontal and vertical direction, plus the restriction in the vertical direction introduced by this roller, we make this structure fixed in the dimensional space, so isostatic. The same thing happened with the cantilever beam, where the fixed support is able to restrict at only one point the displacements in the horizontal direction, in the vertical direction, and any rotation of that cross section. When we have a structure that has more than 3 restrictions in the two-dimensional space, for example, this beam is pin and pin in the two extremes, we are introducing an additional degree, an additional restriction. So we are restricting 4 degrees of freedom when the beam has only 3. This is a case that is called a hyperstatic structure. And in this case, you have an extra degree of hyperstaticity, is called. So this beam have a superabundant restriction that make the structure hyperstatic. The problem with hyperstatic structures from our point of view, when resolving simple structures, is that in order to resolve the reactions, we are not having enough number of equations if we use the equation of equations. Because we have 4 unknowns now, and we have only 3 independent equations of it. This is because this pin support will produce 2 reactions, one in the vertical direction and another in the horizontal direction. The other pin will do the same. So we're going to have 4 unknown and only 3 equations. The same thing happened in this example. For example, this fixed and pin beam. So in this case, you have 2 extra reactions to calculate in here and only 3 equations. So this beam is hyperstatic as well, so able to resolve it with the different equations only. Of course, this structure can be resolved. In order to do that, we are going to use extra equations based on deformations or other principles. But for the moment, we will still dealing with isostatic beams only. Other examples of hyperstatic structures are the ones shown on the screen. This is a fixed beam. This is a fixed and a roller beam. In here, for example, we have some continuous beams. So these beams have superabundant restrictions, so they are all hyperstatics. So we will need more equations to resolve it in terms of in terms of reactions, and after in terms of internal forces and stresses. There are other types of structures called hypostatic structures. These structures suffer the opposite situation as the hyperstatic structure. So in this case, we have less restrictions that are necessary to keep the structure static, let's say, so in equilibrium, stable, fixed in the space. And for example, there is a famous example that is called the isostatic apparent beam. So in this case, apparently we have the beam support located to the left extreme and a roller to the right extreme, but the position of this roller make this structure unstable, because in reality this point can move in the vertical direction. So even when we are introducing enough number of support, the support are not located in the right position to produce the here the stability of the beam. If you have a beam support in the middle of the beam, you are having a beam that is able to rotate around this point, so it's not stable, so it's hypostatic as well, because you are restricting only 2 degrees of freedom of the 3 degrees of freedom that this beam has in the two-dimensional space. The same thing with the hypostatic beam shown in here, and this one, the last one, which is restricted by 2 rollers in the 2 extremes of the beam, allow the beam to move in the horizontal direction. This is the reason why these structures are called hypostatic, because hypo means less, so the 3 degrees of freedom are not restricted. So there are at least 1 degree of freedom that is not restricted, and the beam is able to channel space. The same concepts we apply to cantilever beams and simple supported beam are applied to any structure. For example, if we introduce the concept of frames, so two-dimensional structures that have 2 dimensions in the horizontal direction and in the vertical direction, as an arc, for example, this arc is simple supported as a simple supported beam, so it's a simple supported arc. This structure is isostatic again, because this arc, as a beam, has 3 degrees of freedom, displacement in horizontal and vertical direction, and rotations, and these two, and the combination of the beam support and the roller produce the enough restrictions to keep this structure stable, and we are going to be able to calculate this structure because we have the 3 equations that allow us to write the equations to find out the values of these reactions. This framing here is a frame that is formed by this column, this beam, and this second column to the right is simply supported again, so an isostatic structure with 3 degrees of freedom and 3 restrictions, so we are going to be able to calculate it without any problem. So in order to start the study of the frames, before calculating or introducing the beam frame, we are going to do the analysis of this isostatic frame. So the idea will be to compare an isostatic frame with a 3-pin frame to see what happened in terms of reactions, and what happened in terms of internal forces, and what happened in terms of internal stresses on the cross-section. So in order to do that, we are going to start then with the isostatic frame. So this is simply supported. You have a beam support to at the point A, a roller at the point F. The cross-section is the one you can see on the screen. It's a nice section, and the position of this profile, this let's say it's a steel, to say some particular material, is located in the way you can see in the figure. So these are the direction of the axis in the 3-dimensional space, just to avoid any ambiguity in the way it's supposed to create the. So in order to calculate any structure, as you know, as we did previously with simply supported beams and cantilever beams, we need to first sketch the free body diagram. This is a very important step in order to start the writing of the equations of equilibrium. So we need to choose the direction of the expected reactions, and in this case I have chosen to use these directions for AX and XY, and this direction for BY. The equation will tell us if these directions are right or are wrong, as we are going to see in a few minutes. So once we have the free body diagram, we are able to establish, for example, the summation of moments and just doing the moment. This is the moment of this force, is 15 times 2. This is the moment of the UDL, is the whole UDL, h times 6 multiplied by 3, the distance to the middle of the UDL is giving us another positive moment because it's producing, and minus the moment produced by this reaction we have decided in terms of direction multiplied by the distance, perpendicular distance to the force, which is 6 meters. Working out the value of the reaction, we get 29 kilonewtons. Simple. If we take moments around the point F, we do the same considerations in terms of all the moments around the point, and we can work out the value of the reactions A to Y, which is 19 kilonewtons. So just to mention, regarding the moment around F, this is not producing any moment because there is no distance, perpendicular distance to the force to the point F. The same happens when you take moments around the point A. So these two forces not produce any moment because there is no perpendicular distance to the force regarding the point. So we have now the values of these two vertical reactions located in our free body diagram. So it's always a good idea to use an extra equation of equilibrium, for example, the summation of forces in the y direction or vertical direction, to check that this equilibrium that direction is equal to 0. So this equation can help us to identify some errors we could make in the summation of moments, but in this case the summation of moment were frankly well done because the summation of forces in the x direction is equal to 0. So we have certain tranquility that these calculations were made correctly. Using the summation of forces in the x direction or horizontal direction, we have 15 kilonewtons direction plus ax, and we notice in this equation that the directions could be a minus 15. So this means that the 15 kilonewtons is definitely the value of this reaction, but this minus in here indicates that the direction of this reaction is actually in the opposite direction, so it's going to the left. And this makes a lot of sense because, of course, the reaction needs to compensate the horizontal force, the only one we have on this structure that is right. So evidently, the reaction needs to go to the left to cancel this value and to keep the frame in equilibrium in the. So once we have the reactions of our frame, we are in good position of studying internal forces, and we are able to, for example, sketch the shear force diagram. So we are going to use, so I'm going to use the technique checking the structure from left to right. So I will start at the point A. 15 kilonewton we have at that point. The horizontal force will be the shear force for the cross sections that are horizontal in this column from A. So the first force is 15. The shear force will be constant from A to B and will be close with the load applied to the structure of 50 kilonewtons. And in the rest of the length of this, or the height of this column from B to C, you see if you do the summation of shear forces to the left is equal to 0. If you do the summation of shear forces to the right, for all the horizontal forces is going to be equal to 0. No shear stress from B to C. In the beam CE, we start with the reaction 19 kilonewtons after we consider the reduction of the shear force produced by the UDL in a way until we reach the last point of the beam, and we close the diagram with the reaction 29 kilonewtons. And this is the shear force diagram for the beam. If we check the second column, EF, we notice that the summation of shear forces, or horizontal forces in this case, to the left or to the right is equal to 0, so there is no shear forces on the column to the right. Once we have the shear force diagram, we have this particular point that is very useful to locate the position of the maximum moment, because we know there is a relationship between the shear force function and the bending moment function. So where the shear force is equal to 0, the bending moment will be maximum. So we need to calculate the location of that point. In order to do that, we are going to use between equivalent. So we have a triangle and small triangle of 19, 8, and the unknown base. And we have this big triangle of 48 for 8 and 6 for the base. So applying the relationship of these two triangles, we work out the value of the location of the maximum moment. So now we know that the maximum moment will be at 2.375 meters from the point C, let's say the start point of the beam on top of this frame. Another thing we can do when we have the shear force diagram is to calculate the maximum shear stress. So we have the cross section for the beam where we have the maximum shear force. We know the distribution, the parabolic distribution of the shear stresses on the cross section and the location of the maximum in correspondence with the neutral axis of this cross section. So we only need to calculate the moment of inertia for the cross section of an ice section, and we need to use the expression for the calculation of the shear stress, where we have the maximum shear force, and we have the moment of area of this T in this case, that is split in the moment of area of the flange and the moment of area of the web of this cross section, and we have to divide by the moment of inertia and the value of the width of the cross section at the location where we're calculating the shear stress. And in this case, we obtain 36 Newton per square meter as maximum shear stress for this frame. In order to calculate the moments, it's always a good idea first to locate the point of interest. Will be the location of the reactions, of course, the location of any concentrated or punctual force applied to particular points in the frame, the start point and the end point of the UDL, as well as these corners that are in correspondence with the initial and final point of the UDL. The middle of the UDL could be a point of interest as well, so we are going to use it. And after that, the only thing we need to do is to, so using the definition of the moments, doing the summation side of the structure, for example, we get the moment at A is equal to 0, because this is basically the moments at the point B is just the moment produced by 15 kilonewton, the horizontal reactions multiplied by 2, and it's positive because it's clockwise. The rotation produces clockwise around B. And in the diagram, of course, we are going to follow the same convention beams. So if the positive moments are the moments under a beam, for this column, by continuity, the positive moment will be to the right. So the moment at point C is going to be 15 kilonewtons times 4 minus 15 times 2 is 30 kilonewton per meter. The moment at the point D will be 19 times 3, which is the moment produced by the vertical reaction, 15 times 4, the moment produced by the reaction, minus 15 times 2, the moment produced by the external force, and minus 8 times 3 times 1.5 is the moment produced by the portion of the UDL from the point D to the left. The total moment will be then 51 kilonewton per meter and will be sketched under the beam because it's a positive moment. We can check doing the summation to the right side of the structure to check the moments at D, and we found the same value, and the moment at E and F are equal to 0 because there is no any force producing any moment around those points. So this column is free of moments in this particular frame. So once we have all the values of the moment, we can sketch the bending moment diagrams, and this is the results. And we can use the distance we have worked out from the shear force diagram to locate the maximum moment, and just doing the moments of the forces we have at the location of maximum moment we have calculated using the shear force diagram, we get the maximum moment equal to 52.6 kilonewton per meter. This will be useful for us to calculate the maximum bending stress. As you see, all the moments calculated for this frame are positives, and this is the reason why all the sketches were made internally in this frame, because in a frame like this, in the interior of the frame and exterior. But we only have positive moments in this frame. And a mention about this corner. In this corner we have moments in the column and we have moments in the beam. And if we magnify this corner, what we need to realize is that the moments have opposite directions, and these moments cancel one to each other because this corner, as every corner in every structure, need to be in equilibrium. So this corner is in equilibrium because these two moments in the column and in the beam, and the corner E is in equilibrium because the moments are equal to 0 in both, in the beam and in the column. So we can calculate, we calculated already the moment of inertia of this beam, so we can calculate as well the maximum bending stresses using the maximum bending moment expressed in Newton per millimeter. 60 millimeter will be the maximum distance from the neutral axis to the farthest fiber on top or at the bottom of this I section, divided by the moment of inertia. We got plus or minus 733 Newton per square millimeter is the maximum bending stress for this frame, and is located in the location of the maximum moment. In terms of axial forces, if we study the free body diagram with the values of the reactions, we can identify these compressive internal forces on the columns. The maximum is 29, so we can calculate the area of the cross section, we can calculate the maximum compressive stress, and it's equal to minus 14.5 Newton per square millimeter, and this is the distribution, uniform distribution along the cross section. So this is the end of the analysis of the isostatic frame. Now, if we, for some reason, we need to consider this frame with two pins at the bottom, so we don't have any more pin support and a roller, but two pins. This structure becomes a hyperstatic and not calculated. But what we can do to use the equation of equilibrium is to introduce an extra hinge in the structure, for example, on that corner in here. So this will divide the frame in two. So we are going to have 3 degrees of freedom for these columns and 3 degrees of freedom for this L in here that form the rest of the frame. So this hinge we have introduced will restrict the movements in the horizontal and vertical direction, so restricting 2 degrees of freedom, and these pin supports will restrict 2 degrees of freedom each. So at the end we are going to have an isostatic frame because we have 6 degrees of freedom and 6 restrictions. Having an isostatic frame will allow us to use the equation of equilibriums and extra equations of moments around this point C, because this hinge allow rotations, will define a point where the moments are equal to 0. So we can take the summation of moment to the left and to the right to establish the values of the horizontal reaction, as we are going to see in a minute. So this is the free body diagram for this 3-pin frame now. So we are going to have horizontal reactions in this pin support and in this pin support. The summation of moments around the point A and F will be in the same way as before, getting the vertical reactions. This is exactly the same. And in order to establish that these calculations are okay, we use the summation of forces in the y direction for the whole structure, and we check that the reactions are okay. When we want to use the summation of forces in the horizontal direction to establish the value of the horizontal reactions, we find that there is 2 unknowns and only 1 equation, so we cannot resolve this equation. But we can use the summation of moments at the point C that is equal to 0 by definition, because this is a hinge that allows rotation, so So during the summation of moments at the point C to the left, we can work out the value of the reaction AX, and doing the summation of moment at C to the right, we can work out the value of the reaction, horizontal reaction at the point F. So in this way, using these additional two equations that this hinge has allowed us to write, we are able to resolve the structure in terms of reactions. But again, this is only possible because this structure is isostatic. If we have a hyperstatic structure, we will need to use extra equations, virtual principle of forces or displacements or something like this. So once we have the reactions, again, we are able to produce the shear force diagrams as usual. And what you notice in this case is that the shear force for this structure is different to the one we calculated for the isostatic frame. So as a consequence of the introduction of this pin support to the second column and the hinge in the middle in this corner, has produced a variation of the internal shear force distribution. So these changes and these assumptions are not for free as usual, so we are producing changes, and we have, for example, shear forces where in the previous case we have none, and the distribution of the shear force is different because, and the values are different because this changes. The beam remains the same in terms of shear forces, so we can continue now with the calculation of the stresses. For example, there wasn't any change in terms of the maximum shear force, so there is no any change in terms of the maximum shear stress neither. If we calculate the moments, we realize that the moments have suffered changes as well. So we calculate the moment at every single point again for this beam, and the maximum, not the maximum, the maximum moment at the point of interest has changed from 51 to 21, for example. So, but we are going to see in a more clear way the differences if we sketch the diagram. So now the distribution of moment is different in this column. Big moments appear in the second column, and the bending moment diagram is not all positive anymore, so we have areas with negative moment, and actually the maximum moment is 30 now and located in this corner instead of being located in this position as in the previous example. We have a maximum moment at the beam that we can calculate as well. There is an interest as well as the maximum bending moment at that location for the beam, but the maximum moment of the frame is located at the point E, as I said before, and the maximum bending stress will be this plus minus 418 Newton per square millimeter, and the distribution is the one you see on the screen. In terms of axial forces, there is no any change because the columns are subjected to the same compression with the same value. So in the column EF to the right of the frame, what we have is a combination of compression of 29 kilonewtons as an internal force and a bending moment that is linearly distributed from 30 kilonewtons per meter on top to 0 at the bottom of the column. So in terms of the stresses, these internal forces produce at the point where these efforts are maximum a compression of 14.5 Newton per square meter, and a linear distribution of bending stresses of as a maximum of 418 in compression in one side and 418 in tension in the other side. So we need to combine these two stresses to have the total stresses on the cross section, combining compression and bending stresses. So this is what I did in here. So basically in one extreme you will have minus 433, and in the other extreme you will have plus 404. So you will have a distribution of combined stress like the one on the screen that I'm circling right now. And you notice that the 0 will be not in correspondence with the original neutral axis of the cross section anymore, but you have moved because the combination of compression and bending stresses the neutral axis to a new position. Okay then, so we have calculated these two frames. The first one is an isostatic frame because we have a pin support and a roller, so it's a simple supported frame. And the second frame is isostatic as well, but have at the end, at the bottom of the columns, two pin supports and have a hinge in the corner C. Many times when we are resolving structures, and because these structures are connected with the reality, we need to choose what is the best scheme to resolve and what is the best scheme in terms of similarity with reality. When we have certain limitations, for example, in this case, we don't know how to resolve hyperstatic structures, we tend to use simplified schemes in order to run these calculations with the limitations we have in terms of knowledge in this case, because we are just using equilibrium equations. But they are valid anyway, and the only thing you need to realize and you need to understand is that these structures are similar to reality but are not exactly the reality. So this is the reason why we need to find the best scheme for every particular problem. The other thing is that every change you introduce in your structure in terms of hypothesis or in terms of supports or in terms of loads will change as well the results and the distribution of internal forces and then the distribution of the internal stresses on the cross sections. So in here, for example, we are going to see that in comparison, the simple supported frame and the three-pin frame have a different distribution of shear forces in the column. So initially in the simple supported frame we have shear forces from A to B only, and the value is 15 kilonewtons. For the three-pin frame we have less shear forces on the column from A to C, but the value is 7.5 only, and there is shear force from B to C. In comparison with the first structure from B to C, there is non-shear force. The beam that is part of the frame from C to E have the same shear force distribution and the same values. The maximum is the same. But in the second column from E to F, we have a shear force of 7.5 constant along the edge of the column, and we had none in the first example. So definitely the introduction of this pin support instead of a roller and the hinge in the corner has produced a difference on the columns. If we compare the moments, the distribution of moment of these two structures, we notice that in the first case we have only positive moments, and we have a big moment. The maximum moment is 52.6 kilonewton per meter. And in the three-pin frame, we have changed the distribution of the moment. For example, in the column is not as in the simple supported frame, so it's less moment in the column, the first column from A to C. The distribution of moment has changed radically in the beam because we have reduced the moment, the positive moment, but we have introduced a negative moment equal to 30 kilonewton per meter. And there wasn't any moment in the column, the second column F, in the first simple supported frame, but there is now a linear distribution of moment in there with a maximum of 30 kilonewton per meter, which is in fact the maximum moment in the whole three-pin frame. So again, it is important to understand that the modifications in the restrictions we introduce to our structures, and of course the load we apply to our structure, will produce changes in the distribution of internal forces and the distribution of stresses. And this is because we are changing basically the reactions, and because we change the reaction, we are going to change the internal forces and the stresses. So this was the comparison between these two structures. And one more thing I was about to forget is that if you compare the axial forces for these two structures are exactly the same, But what is not the same is the combination you have between the axial forces and moment, which is the combined stress we have studied for columns. So in the first case, you have in the first column a combination of moments and axial forces, but in the second column you have only axial forces for the simple supported frame. For the three-pin frame, you have combined stress in both columns, but the worst scenario, let's say the worst conditions in terms of combination of internal forces is the compression of 29 kilonewton plus the moment of 30 kilonewton per meter on the column EF. When we are doing this analysis of frames, the analysis, of course, is more complex than the one made in beams, but you can apply all the knowledge and all these methods you have applied in beams to frames as well. And if you notice, the behavior of this beam that is part of the frame is exactly the same as the beam you have studied before. So thank you very much for watching.